What's up, guys? Today's video is on exponential functions, and I'm going to try to cover all of the basics of what an exponential function is, how we graph it, how we find the characteristics. So it may run a little bit long, but we're going to try to cover all the basics of exponential functions in one video. An exponential function, at its simplest form, is where the x is in the exponent. That's why we call it that. This says y equals a times b to the x. A and b are just numbers. And there may not even be something here for the a. You could actually just have b to the x. It could be that simple. Some number with x being the exponent. You may also have something added or subtracted out here at the end, which is not written down. You could also have something added or subtracted directly in the exponent to the x. And when we start graphing, we'll see how that affects the graph. But for now, we really want to focus on this b, which is the base. And b has to be greater than 0, so it can't be negative. And it also can't be equal to 1. If it were equal to 1, remember that 1 to any power is just itself. So this would actually just be a flat graph if b were 1. And if b were negative, a negative number raised to different powers, and remember that x is changing over time, then as you change those powers, negatives have a tendency to flip from positive to negative, positive, negative, and back and forth. And so you get a really disjointed looking graph. So exponential functions have to have a base which is greater than 0, and it can be equal to 1. And there's two particular cases for exponential functions based on what the base is. And we call those two cases growth and decay. If the base is greater than 1, that's a growth function. If the base is between 0 and 1, then it's going to be a decay function. And sometimes we'll say that shorthand, we'll just say less than 1. But remember, it can't be less than 0. So another way to say is between 0 and 1. Okay? And we'll see some examples in a minute. But here's what that looks like. A growth function is going to look like this. It's going to increase as it goes to the right, and it's going to approach an asymptote as it goes to the left, which is usually going to be the x-axis, but not always. For decay functions, it's the exact opposite. It's mirror flipped left to right. The part on the left is flipped to the right, the part on the right is flipped to the left, so that you get a graph like this, which goes up to infinity as you go to the left, and approaches the asymptote as you go to the right. So here's some common characteristics. The domain is all real numbers for any exponential function, because you can plug in any number you want for x. That means the graph is going to go as far to the right as you want to go, and it's going to go as far to the left as you want to go. It will go left and right forever in either case. You can plug in anything you want for x. The range is never going to be all real numbers because it's always going to have an asymptote. So in these pictures here, the range would be anything greater than, from here up, from the asymptote, and anything above that. And the same thing over here, from the asymptote up. And most of the time, this is how exponential functions are going to look. Now, there is a special case where an exponential function could be flipped upside down. So going from this position, it would actually be flipped, and it would go from the asymptote going down, or from the asymptote going down. Very uncommon, and certainly in this class we're not going to see it very often, but just like any function, that can happen. And the way it happens, like every other function, would be if the leading coefficient of the function was negative. If I put a negative sign out here, just like any other graph, it would flip it vertically, like this. But that's fairly uncommon. I don't think we'll see very much of it. Okay, so the asymptote, as I said before, usually is the x-axis. It's usually going to approach the x-axis and get closer and closer and closer, but never reach it. What would change that is, again, like every other function, if at the end of the function you add or subtract some number to the end of the function, that shifts the graph vertically. If you remember your transformations from previous classes, adding and subtracting on the end of a function will shift the graph up or down by that many units. So if, for example, you had a plus 5 at the end of your graph, that's going to shift your asymptote up 5. So instead of being at the x-axis, your asymptote would be at 5. Y equals 5. It would raise the graph up. And similarly, if you were to subtract a number, like maybe you said minus 2 at the end, then the asymptote would be negative 2. It would shift the graph down 2 units, and it would now approach negative 2 instead of approaching 0. So the asymptote is not always 0. A lot of people say that it is, but it's not. Exponential functions can actually have something added at the end, and that's what would happen. Okay, so those are the things that they both have in common. Now, where they get different is when you start talking about a couple other things. So, first of all, growth, the graph is increasing. Decay, the graph is decreasing. Well, what that means in terms of end behavior is, for growth, as x approaches infinity, f of x approaches infinity. As we go to the right, the graph goes up. As x approaches negative infinity, f of x approaches whatever the asymptote is. In this case, it approaches 0. Again, if the graph were shifted somehow, it would be approaching whatever that asymptote is. And it's the opposite here. As x approaches infinity, as we go to the right, f of x approaches the asymptote. As we go to the left, f of x approaches infinity. It's important to remember that while this is approaching the asymptote, it gets closer and closer to that number, but never gets there. It's still decreasing. No matter how far to the right you go, this graph is decreasing as you go to the right. However, it still will never get below the asymptote. So instead of saying it approaches negative infinity, we say it approaches the asymptote. Okay, here I have an example problem that's similar to one that's in the homework 1 worksheet. So here's a function, and they're going to ask you some questions and then ask you to graph it. So the first thing they're going to say is, what's the base? What is the base of this function? So the base is the number that's underneath the exponent. Is this number here. So that number is 2. Is it growth or is it decay? Because the base is bigger than 1, it's going to be growth. And the reason for that, remember, if this number is bigger than 1, what happens when you multiply it by something bigger than 1? It makes the number get bigger, right? So that's why as you go to the right, the graph gets bigger. If you multiply by something less than 1, what usually happens? Like, what happens if you multiply by a half? It makes a number smaller. That's why as you go to the right on the graph, it gets smaller and smaller and smaller. So bigger than 1 means growth. If this were less than 1, like a half or a third or a fourth, then it would be decay. And so now to make the graph, just like any function, you can always make a graph by plugging into a table of values. And you can actually type this into your calculator and go to the table button and it will do this for you. But it's good practice to go ahead and get used to plugging some of these numbers in, just to kind of remind ourselves what happens. So I like to go a little bit to the left of 0 and a little bit to the right of 0. So I went to -2 and 2. So I'm going to plot the points between here and here. And maybe I'll throw some extra ones in there. Even though I numbered it that way, I actually want to start in the middle because it's a little bit easier. So 0 is the easiest thing to plug in. What would be 2 to the 0 power? In other words, we're going to do 3 times 2 to the 0 power. 2 to the 0 power is 1. So that's really 3 times 1, which is 3. Okay, so I can go ahead and put that on my graph. 1, 2, 3. That's the point 0, 3. When I plugged in a 0, I got 3. Okay, let's plug in a 1. That'll be easy, right? So 3 times 2 to the first. That's 3 times 2, which is 6. Okay, so we can plot that. 1, 1, 2, 3, 4, 5, 6. There's the point 1, 6. Now anything to the right of this is going to be off my graph. I'll go ahead and put it on the table though. 3 times 2 to the second power. See, only the x is changing. 2 to the second is 4. So this is 3 times 4, which is 12. And I'm not going to plot it because it is going to be off the graph. Okay. As I go to the left, I'm going to plug in a -1 here. So 3 times 2 to the -1. Well, if you remember your exponent rules, and you should, anything to the -1 power means you flip it upside down. So what you've got is 3 times 1/2. 3 times 1/2, which is about 1.5. It is 1.5. You could also write that as the fraction 3/2, 3 over 2. So at -1, I'm going to go up to 1.5, which is right about here. Okay, then I'm going to plug in -2. I'll flip it upside down and square it, so I get 3 times 1/4, which is 3/4 or 0.75. Either 3/4 or 0.75, however you'd like to write it. -2, we're going to go to 0.75, so it's about right here. Okay, now I'm satisfied with these points, so I'm going to go ahead and draw the curve through these. Now remember, we don't connect the dots, we kind of just draw a curve through them. Then as we go to the left, we're just going to approach the asymptote, just get closer to it like this. And that's a pretty good sketch. Didn't really go through that point very well, but you get the idea. It's a pretty good sketch of what the graph's going to look like. And here's another example, like one that you're going to have on your homework, and it's going to ask a few different questions, but we're still largely doing the same thing. So let's just take a look at it. First of all, it wants to know the domain. Well, if you've been paying attention, then you know that the domain for any exponential function is going to be all real numbers. Similar to the polynomials we did recently, all real numbers. The range is going to go from the asymptote up, unless it's been flipped upside down, and it hasn't. It's going to go from the asymptote up. So really, you might want to answer the asymptote question first. And so really, have you added or subtracted anything out here? Have you done anything that's going to make it shift up or down? If you haven't, and they didn't, then the asymptote is going to be the x-axis, which is y equals 0. So if this is the asymptote, the graph's going to go up from there, then the range is y is greater than 0. Notice that I don't put an equal sign on there because remember, the graph will never actually reach 0. It'll get closer and closer and closer to 0. In fact, this graph's going to go this way. But it will get closer and closer to 0 without ever actually hitting it, so I can't put an equal sign on there. Now for the intercepts, remember that and there's some rules and some kind of tricks here, but I really like to just emphasize that when you go to find an intercept, all you have to do is plug in 0 for the other variable, regardless of what kind of function you're looking at. So what does that mean? Well, that kind of depends on the type of function you're looking at. So x-intercept, we're going to plug in a 0 for y, meaning the whole left side of the equation, I'm just going to put a 0 there. And then I need to work this out however I can. Okay, so the question you have to ask yourself is, what power of x is going to make all of this equal 0? Well, I can divide both sides by 2, and that's just going to give me 0. Okay, so I can divide the 2 over here, which is 0. Now the question is, what power of 0.5 is going to give me 0? What power can I raise this to that will give me 0? The answer is there isn't one. Okay, so there is no x-intercept. Well, you might realize this already because the asymptote, as we said, was going to be 0. Now, I haven't graphed it yet, but the graph's going to go like this. If we know that the asymptote is 0, that means it's never actually going to cross the x-axis, so therefore there is no x-intercept. There's not going to be an x-intercept unless the graph were shifted down. If the graph were shifted down, you'd have an x-intercept because the graph would cross the axis. We're not really going to see any examples of that, at least not yet. So we can ignore that for now. So most of the time, the x-intercept is actually going to be none. Now the y-intercept is always going to happen because remember the graph goes left and right forever. Wherever it goes, however it's shaped, it's going to go left and right forever, which means it has to cross the y-axis somewhere. When it crosses that y-axis, that's going to be the y-intercept. So again, going back to my rule, anytime you look for an intercept, you plug in 0 for the other variable. Well, what does that mean? Y-intercept, plug in a 0 for x. So I can say f of x or y equals 2 times 0.5, and I'm just going to plug in a 0 for x. Well, that's just 2 times 1, because anything to the 0 power is 1, and that gives me 2. Okay? We would also have found this, let me write it in here, 0, 2. We would have found that as we were graphing it as well by filling out the table. Okay? So 0, 2, we already know is a point on our graph. Okay, so now that we have the table, we can use that to make our graph. We already plotted 0, 2. I can plot the point 1, 1. I can plot the point 2.5, which is right about here. Okay, so you can see it already approaching that asymptote. As we go this way, at -1, we got to plot a 4. As we go to -2, it's going to be 8. 2, 3, 4, 5, 6, 7, 8 right here. Okay, so you see it's climbing very quickly as you go this direction. And that would be our graph. Okay, so now that we have the graph, let's consider the end behavior. And this part's pretty easy once you have the graph. As we go to the right, what is the graph doing? It's approaching the asymptote, which is 0. So as x approaches infinity, f of x approaches 0. As x approaches negative infinity, as we go to the left, f of x is going up, so it's approaching infinity.